All right, so this is chapter 11, and we're going to be talking about the states of matter. Hopefully you know a little bit about this, but hopefully you'll also learn a little bit more. All right, so let's compare gases, liquids, and solids. You probably know some of this from, probably even from elementary school. So we know that gases are compressible. So just a couple other things. They fill the container. They're fluid. They fill the container to totally whatever container they're in, they'll fill it completely. The reason this is because their molecules are widely separated. So liquids are relatively incompressible. If you've ever tried to fill a bottle to the tippy top and put a lid on it, you're not going to be able to push the water molecules much closer together. Their molecules are much more tightly packed, close together. And then, of course, solids are nearly incompressible. They're very rigid. Back up. Liquids will take the shape of the container, but only to the point where they fill the container. They won't expand to fill the container the way gases do. Solids have their own shape. They're tightly packed in close contact. Other molecules are all in very close contact together. Generally speaking, gases are pretty light, not very dense. Liquids tend to be more dense than gases, and in general, solids tend to be more dense than liquids because density has to do with how much empty space there is. And gases have a lot of empty space. Liquids have a little bit of empty space, and solids have very little empty space. All right, so we can kind of see some pictures here. And if you get a chance, you might watch the YouTube videos, but it's basically showing you the difference between gases, liquids, and solids. So gases, as you can see, are very far apart. Molecules are moving quickly. In liquids, molecules are still moving, but they're being held closer together. So there's not a lot of empty space between molecules. And then a solid is a much more rigid, organized pattern. Not always, but often, and contains its own shape. And so you can see what we've been talking about. All right, so we're going to talk first about gases. So we learned that gases are a collection of widely separated molecules, and they're in constant chaotic motion. And generally speaking, the kinetic energy of the molecules kinetic energy, as we know, is related to temperature. And so the higher the temperature, the higher the kinetic energy. But in general, the kinetic energy of the molecules is much larger than the energy of attraction. So what does that mean? Molecules are not very molecules are, and we'll talk about this in a little while some more too. Molecules are attracted to each other. We'll talk about types of attractions later, but in general, molecules tend to be attracted to each other, but because they're moving, they have a lot of energy, and the kinetic energy keeps them apart. So it's kind of the phase that something is in will depend on this balance between the attraction between the molecules and the energy or the speed of the molecules. So for gases, the kinetic energy is much larger than the energy of attraction, and so they stay far apart. And so that's why the gases can expand to fill their container, because even though they might be attracted to each other, the movement of the molecules is much more to keep them pulled apart. So liquids, on the other hand, have stronger attractive forces. So the forces between the molecules are strong enough to hold the molecules close together, and the kinetic energy is not enough to pull them apart. So molecules tend to be close together. That's why liquids tend to be more dense and also less compressible than gases, because of course gases, you can compress them down because there's lots of empty space between them. But liquids, being in the intermediate, the intermolecular attractive forces are not strong enough to keep molecules from moving past one another. So that's why liquids are a bit more random than solids, because the attractive forces are not strong enough to hold them rigidly the way that solids are. So that brings us to solids. Intermolecular attractive forces are very strong, and they hold the molecules close together, close to each other, and almost lock them into place. They're still moving, but they're almost locked into place. And so because solids are held so closely tight together, there's very little free space between them, and so they're very incompressible. You can't compress them any more than they already are. And also, this is why they're rigid, because, or why they're more dense, because they have very little space. It's really packed tight. Generally, not always, but often solids form highly regular crystalline patterns, although they can have more of an amorphous pattern like glass or something like that. And just keep in mind that even though solids don't have a lot of kinetic energy, they still have some energy, and they do vibrate in place. So there's still movement. As long as the temperature is above 0 degrees Kelvin, which is 273 Celsius, all molecules have some energy, and there is some movement. Movement and energy are the same thing, or are related to each other. All right, so like I said a little bit ago, the state a substance is in will depend on the balance between the kinetic energy, the energy of movement, how fast molecules are moving, versus the inner particle energy of attraction, or how strongly are the molecules attracted to each other. All right, so we've got attraction, keeping them held together, and we've got movement, keeping them moving farther apart from each other. And so it should make sense to you when we talk through this that, you know, gases tend to be at higher temperatures, or if you're thinking about the same substance and you're going solid, liquid, gas, of course the gas will be at higher temperatures because there's a lot more kinetic energy keeping the molecules apart, whereas solids tend to be at the lower temperatures where molecular movement is slow. All right, so that's what I was just saying. Inner particle attractions draw molecules close to each other. Kinetic energy keeps them apart because the molecules have energy and they're moving. And again, kinetic energy depends on temperature. So by changing the temperature, we can change the state. And you already knew that. All right, so let's first talk about what are the names of the changes of, and again, hopefully you at least know the majority of these. So what happens if you want to go from a gas to, let's see, from a liquid to a solid? A liquid to a solid is called freezing. A solid to a liquid is called melting. What about gas to liquid? A gas to liquid is condensation, or liquid to gas is evaporation or vaporization. And then you may not know the name from a gas to a solid, but a solid turning into a gas is sublimation. It does not go through a liquid phase. It goes straight from a solid to a gas, like a dry ice. And then if you want to take the gas and form a solid without going through the liquid phase, that is called deposition. So you should just know those names, and you probably already know most of them. Okay, so let's talk a little bit about something called vapor pressure. Liquids are continuously vaporizing even at temperatures lower than the boiling point. And you've experienced this to some extent, probably if you've ever opened your gas tank and you hear a kind of a whoosh, that's the vapor pressure escaping your tank. And so a vapor pressure is a vapor above a liquid. However, it's a liquid that's not boiling. Actually, solids can have a little bit of a vapor pressure if they go through sublimation, but mostly it's liquids. So let's talk about kinetic energy and the speed of a molecule. We already know that if the faster a molecule moves, the more kinetic energy it has. But when we say, if we have a molecule at a particular temperature, it has an average kinetic energy. So this graph here, what you can see is, I don't know exactly what molecule it is, but it's showing that, let's say at a negative 100 degrees, you can see the red line shows that the average speed of the molecule is about 300. However, notice that some molecules are faster than 300 meters per second and some are slower. So the red line shows, or under the curve is the number of molecules. So of course the average is right at 300, but some move slower, some move faster. If you increase the temperature, and you can see in the green line, the green spotted line, to 20 degrees Celsius, again, the average, the top of the hump, is right now about 400. So on average, all the molecules are moving faster. However, we still have some that are moving slower than 400, some that are moving faster. Some, if you follow the green line, we even have some molecules moving 1,000 meters per second, even though the average is only 400. And then again, if you increase temperature up to 600, you can see that your average has increased, so it's now around 700, but we still have a wide range of molecules. So some molecules are moving faster than others, even at a lower temperature. So we still have some moving above 600 even at negative 100 degrees, but we of course we have a whole lot more above 600 meters per second at a higher temperature, but we still have some at every temperature. We have some faster molecules, some slower molecules. And so the average speed in general is slower at lower temperatures, but there can be some molecules with enough energy to escape the liquid, and that's the key. They might have enough energy to pull away from the liquid, even if it's not at a boiling point temperature. So the molecules that have enough energy can escape the surface and they go into the gas phase. If the vessel is open, like the one on the left, you can see that the molecules move away and evaporation takes place. If the vessel is closed, what happens is that the molecule will leave the surface of the liquid and stay in the space above the liquid, and that's called vapor pressure. And this is not the same thing as boiling, because we're not at a boiling temperature. This is just a few molecules that have enough energy to escape the surface of the liquid, and so they float around in a gaseous form above the liquid, and that's called vapor pressure. So a more formal definition, the vapor pressure of a liquid is the partial pressure of the vapor over the liquid measured at equilibrium at a given temperature. So you can imagine that vapor pressure will increase with an increasing temperature because you have more molecules that can escape. But the interesting thing is, if you're at a constant temperature, an equilibrium is set up. So you have enough molecules, you have some molecules that have enough energy to escape, but then actually if they're floating around in the space, in the air above the empty space above the liquid, sometimes they'll slow down and they can be captured again by the liquid. So you're going to have some molecules escaping, some being attracted back to the liquid, and an equilibrium is set up. So the number of molecules in the vapor will pretty much stay constant. So you'll have a particular vapor pressure at a given temperature. Now, if it heats up, you can have more molecules escape, and so then your vapor pressure will build. But still, an equilibrium will be set up where you'll have about the same number of molecules in the vapor at any one time, even though some may condense and some may evaporate again. So again, this is at a liquid at lower temperatures than boiling point. You have something called a vapor pressure. You can measure this is showing how they can measure vapor pressure. Here they're putting a liquid into a column of mercury, putting some water in there, and they're showing what the top of the mercury column before the experiment, and then they put the water in there, and you can see that the mercury has fallen even more, and so the difference between where the mercury was before the water was added and after the water was added will give you the vapor pressure, the pressure due to just the molecules in the gaseous phase. So what are some things that affect the vapor pressure? We've already mentioned temperature. Temperature is will change the vapor pressure quite a bit. If the temperature increases, that means the average kinetic energy of the molecules increases. And as we saw on that chart earlier, more molecules will be above the threshold, will have enough energy to escape the liquid. And so if more molecules are in the vapor phase, we'll have a higher vapor pressure. We haven't talked about boiling point yet. We're going to come to that in just a minute. If a compound has a high vapor pressure, it generally means that it will boil at a lower temperature. So vapor pressure and boiling point are actually inversely related. But again, we'll talk about that in a little while. Vapor pressure will also depend on the molecular attractions, probably not quite as much as temperature, but they do depend on the molecular attractions. If a substance has weaker attractions, it will have a higher vapor pressure because more molecules. You won't need as much energy to pull them apart from each other. So higher vapor pressure is related to weaker molecular attraction. So liquids and solids that have relatively high vapor pressure at normal temperature are said to be volatile. That's just a word. And they tend to actually have, so if something has weaker attractions, they will have a higher vapor pressure and they will have a lower boiling point. And they're said to be volatile because they tend to have a very high vapor pressure. Okay, so boiling point. Now, the temperature at which the vapor pressure of a liquid equals the atmospheric pressure surrounding the liquid, we are at the boiling point. So if you can picture it, you have molecules that, if you're heating up a liquid, heating it up, the more you heat it up, the more kinetic energy the molecules have, and so the more molecules that can escape the liquid phase into the vapor phase. And again, we're not at the boiling point yet, so it just means that there's a bigger proportion of molecules that have enough of that threshold energy to escape the liquid. So we know that the vapor pressure will continue to rise. So at the temperature where the vapor pressure equals the prevailing atmospheric pressure around the liquid, the water will begin to boil. So again, as the temperature increases, vapor pressure increases. When it reaches the atmospheric pressure surrounding the liquid, it will boil. Stable bubbles of vapor will form within the liquid and they will then rise to the surface and called boiling. Now, the normal boiling point, when I say water boils at 100 degrees, I'm not being totally truthful. When I say water boils at 100 degrees, what I mean is at standard atmospheric pressure, which we know is 1 atmosphere pressure. So we call that the normal boiling point. That's usually the boiling point that you find in literature or in charts and things like that. So the normal boiling point is the temperature, the boiling point, the temperature that water boils at, or whatever the liquid is, boils at 1 atmosphere or at standard pressure. So that's not always the same temperature. Water can boil at different temperatures depending on what the atmospheric pressure is. So we'll look at that a little bit more closely. But the normal boiling point is the boiling point at 1 atmosphere pressure. So boiling points are directly related to the atmospheric pressure. If the atmospheric pressure is a little bit lower than standard pressure, then the boiling point of the liquid will decrease. If the pressure increases, the boiling point will increase. So let's look at an example. Let's say you live in Colorado, or actually Abingdon, which you'll see in a minute. If you live in the mountains, atmospheric pressure is a little bit lower than sea level. So if, for example, Colorado, if you're at a high altitude, the atmospheric pressure is only about 0.85 atmospheres rather than 1 atmosphere. And so what happens is, because the vapor pressure of the liquid will equal that lower atmospheric pressure sooner, the water will boil at a temperature lower than 100 degrees, because you'll be at the atmospheric pressure sooner, so it will boil lower. Now, that means that you're going to have to cook your food a little bit longer because the temperature of the boiling water is a little bit lower. So if you were to, and I think we do a lab, you may get to do it, where you boil some water, and if you measure the temperature generally around here, around Abingdon, we get a temperature around 98 degrees where it boils. And that's because we're at a little bit lower atmospheric pressure than standard. On the flip side, Pressure cookers are used to speed up your cooking, because what happens is if you increase the pressure around the liquid, you're building up the atmospheric pressure. It's going to take the vapor pressure much longer to build to equal that higher pressure inside the pressure cooker, which means that water, or whatever liquid, but in this case water, will boil at a much higher temperature than normal. So I don't know exactly pressure cooker, but it may boil at 130 degrees rather than 100 degrees. So that means food will cook much faster. So in a regular open pot, you can't cook. The temperature of the water will never get higher than the boiling, whatever it is, at that particular pressure. So here's what I was talking about. So if you're at sea level, yeah, water will boil at 100 degrees because the atmospheric pressure is 1. But if you're a little bit higher elevation, you can see Abingdon has a standard atmospheric pressure of about 0.93, which means water will boil at about 98 degrees. At a much higher elevation, water will boil even lower. So in Colorado, it might boil at 95 degrees. You can see at Mount Everest, water will boil at 76 degrees, much, much lower. So you can't cook it hotter than 76 degrees. And then in a pressure cooker, a pressure cooker may be about 2 atmospheres pressure, which will increase the temperature to about 120 degrees. All right, there's as you can imagine, there's always a heat required with a phase change or a phase transition. If you want to completely convert a pure liquid to its gas at the boiling point, you have to have extra energy to overcome all those intermolecular forces. And so the heat required to boil 1 mole of any pure substance is called the heat of vaporization for that substance, and it's denoted as delta H vaporization. So the amount of heat required to boil 1 mole of any pure substance is called the heat of vaporization for that substance. And that would be at standard pressure. So now what happens if you condense a gas? The opposite is true. So 1 mole of any gas condensed to liquid will actually release the same amount of energy as what was required to go from liquid to vapor. So if it goes from vapor to liquid, the same exact amount will be released, and so the delta H of vaporization to boil it has to be added. If you condense the gas, that much will be released, and so the sign is opposite. So it'll be the negative delta H of vaporization. For water in particular, if you heat up 1 mole of liquid water and want to convert 1 mole of liquid water to 1 mole of gaseous water, it will take 40.66 kilojoules per each mole for each mole. All right, so let's switch gears a little bit and talk about the freezing point. So the freezing point is the temperature at which a pure liquid changes to a solid or freezes. So that's called the freezing point. You already knew that. The melting point, which is actually the same thing as the freezing point, is identical to the freezing point, and it's defined as the temperature at which a solid becomes a liquid. So of course the same thing happens. Unlike boiling points, melting points are really only significantly affected by large pressure changes. So pretty much you can stick with a melting point or a freezing point. We have the similar thing that we had when we were going from a liquid to a gas. So to completely convert a solid pure substance to a liquid at its melting point or freezing point, depending on which way you look at it, again requires an extra boost of energy to overcome the intermolecular attractions. And these, when it's going from a solid to a liquid, are called lattice energies. So the heat required to melt 1 mole of any pure substance is called the heat of fusion, delta H FUS, because you're going from a solid to a liquid. So of course 1 mole of any pure liquid, then when it freezes, it will release that same amount of energy, delta H fusion negative. So to melt it, you have to put heat in, delta H fusion, and then if you, melt it. If you freeze it, you release energy, and it's the same exact amount for 1 mole. For water, the heat of fusion is 6.01 kilojoules per mole. So 1 mole of melting a solid will require 6.01 kilojoules. If you take a liquid water, 1 mole of liquid water, and freeze it, you will release 6.01 kilojoules per each mole. Some examples of this heat of fusion, heat of vaporization. When you have an ice cube melting in your glass of water, you need to put some energy in to melt that ice. Where does that energy come from? It comes from the liquid that you have it in. So what's happening is that the heat from the liquid goes in to melt the ice. The liquid itself then the temperature lowers because it's losing energy. So the water gets colder as the ice melts. A similar thing happens when we sweat. The reason why we sweat is to cool our body off. So if you've got water on your skin and it evaporates, the amount of energy that has to evaporate that liquid comes from your body, the heat on your body. So the energy is taken in to evaporate the liquid water to vapor, and your skin then will lose that amount of energy and you feel cooler. All right, so let's think about what happens if you take some ice at -20 degrees, and keep in mind that we're going to stay at standard pressure for this example. And we're also going to assume that the heating is going to be distributed evenly, and so that's really hard to do. Like, let's say you were putting an ice cube on your stove or something like that. It would be really hard to melt the ice evenly. So keep in mind that we're taking that piece of ice and we're melting it evenly, which means all molecules will heat at the same rate, not the outer ones or the inner ones. So anyway, if you started ice at -20 degrees and you start to heat it, what's going to happen? Well, if you said it's going to melt, you would be wrong. The first thing that happens is that the ice will heat up. So from -20 degrees to 0 degrees, if you add heat to ice, and again, remember we're adding it evenly, so everywhere will just heat up at the same speed. The ice will get warmer, but it will still stay a solid until it reaches its melting point. Once we're at 0 degrees, now if we keep adding heat to it, the ice will begin to melt. Because it's at its melting point, adding heat will melt it. The important thing to keep in mind is that as long as there's ice and liquid, so you've got both phases at 0 degrees, as long as you have both phases present, that temperature will stay at 0 degrees. So melting is an endothermic process because we're adding heat to it. When that heat adds, the temperature does not rise because all of that energy at this point is going into breaking those molecular attractions. The amount of energy required is the heat of fusion. So if we're taking 1 mole of ice, it will take I forgot what the amount was back on the previous slide. The amount of energy will be the amount of energy, the heat of fusion. So again, as long as you have both solid and liquid present, the temperature will stay at 0 degrees. Now, once all that solid has melted to liquid, and we keep adding heat to it, well, what's going to happen? The liquid temperature will increase. And so between 0 and 100 degrees, all we're doing is we're heating up the liquid. So only liquid is present. Once we get to 100 degrees, which we know is the boiling point, now the liquid will start to boil. So at 100 degrees, we have both liquid and vapor present at the same time. And as long as we have both the liquid and the vapor present, the temperature will remain at 100 degrees. Vaporization is also an endothermic process because we're putting heat in. Even though the heat is added, the temperature will remain constant as long as we have both liquid and vapor present. The energy added is the heat of vaporization. The energy needed to completely boil the water is the heat of vaporization. Then what happens after 100 degrees, when after all the liquid has vaporized, if we still have vapor at 100 degrees and then we continue to heat it, what's going to happen? The vapor will just get hotter and the temperature will rise. There's some video links here, so if you go to the regular PowerPoint, not this narrated video, but if you go to this, you can watch some of this happening. And the bottom link is a simulation, which is kind of fun to look at. So you might want to link on that later. All right, so this is what your heating curve looks like, and you can see. So the lines that are kind of tilted to the right are when you only have one phase. So between -20 and 0, we only have the solid. At 0 degrees, you can see that the line flattens and the temperature stays constant, and that during all that process you have both phases present, both the liquid and the solid. Once all of the solid has converted to liquid, again the temperature will rise, so you can see the slope is positive again, and you're going from 0 to 100. And then the temperature will level off at 100, and during that point you have both liquid and vapor present. And then once you have all the vapor converted to steam, all of the liquid converted to the steam, the temperature will rise again. So the flats, when the slope is 0, you have two phases present. When the slope is positive, you have one phase present. If you want to figure out how much energy you need to make all of these things happen, I created this slide because we have to use a different formula for each section. So actually, the positive slope areas come from chapter 6, where you have Q equals SM delta T. So S being the specific heat of whatever you're talking about, the mass, however much of the sample you're trying to heat up, and then delta T is the temperature change. So that's back from chapter 6. So S is the specific heat, which has to be given to you. It's a constant. So if you can see, when you just have solid, the delta H, the amount of heat needed to take ice, for example, from -20 to 0, you would have the mass of the ice times the change in temperature, which in this case would be 20 degrees, times the specific heat of solid, which would have to be given to you or you could look up. The delta H in the positive part from 0 to 100 would be, again, delta H equals M delta T, SM delta T. So S would be the specific heat for the liquid. Delta T would be the change in temperature, in this case from 0 to 100, which would be 100, and the mass. So if you're talking 1 gram or 1 mole or whatever, you would have to convert moles to grams. And then the same thing is true on the just gas part. So delta H is mass times delta T times S. The only thing that changes in this case would be the S, because the specific heat is different depending on if it's a solid, liquid, or gas. But then, to convert how much heat you need to add to change phases, on the flat part, you'll have delta H equals mole times delta H of fusion, which again is a constant that you're either given or you have to look up. Since it's kilojoules per mole, you just multiply by the number of moles. And then same thing for the flat part. When you're boiling something, delta H equals moles times delta H of vaporization. So I think in just a second I do an example. Okay, so let's look at a problem. The heat of vaporization of ammonia is 23.4 kilojoules per mole. How much heat will be required to vaporize 1 kilogram of ammonia? All right, so in this case, all we're talking about is the vaporization. So we just want to know, we're not trying to heat up the liquid or heat up the vapor. So we only have to worry about that. So this is the section that's flat at the boiling point. All right, so it's 23.4 kilojoules per mole of ammonia. Well, we're given kilograms, so the first thing we have to do is convert kilograms to moles. So a kilogram is the same as 1,000 grams. And then 1,000 grams of ammonia, since ammonia is 17 grams per mole, is 58.8 moles. So a kilogram is 58.8 moles. And then we can determine the heat required to vaporize that much ammonia because we know it's 23.4 kilojoules per each mole. So if we multiply by 58.8 moles, we will get 1,380 kilojoules, or 1.38 times 10 to the third kilojoules. So not per mole, because it's 23.4 per mole, but for 58.8 moles, we need 1,380. So problem number 2, how much heat is required to convert 12 grams of ice at -5 degrees Celsius to liquid water at 1 degree Celsius? Now you have to be really careful here, because notice that we have different things happening. And here's just some information. So we know the melting point of water is 0 degrees. The specific heat for liquid water is 4.21 joules per gram degrees Celsius. The delta H of fusion is 6.02 kilojoules per mole. And the heat of fusion, or the heat specific heat for solid water, is 2.09 joules per gram degrees Celsius. So keep in mind, if you want to draw out your sketch, you know that the first thing you have to do is you have to heat the ice from -5 to 0 degrees. And so in that case, so let's see what's it. So from -5 to 0, we're heating ice. So we need to use the equation delta H equals mass times delta T times S for solid. When the ice melts, so once we get to 0 degrees, we have to melt all that ice, and we've got 12 grams of it. So we have to use the equation delta H equals the moles times delta H of fusion. And then finally, we have water at 0 degrees, and we have to heat it up to 1 degree. So we have to again use delta H equals SM delta T, mass times delta T times the specific heat of liquid. So you have to break it down and look at each segment of the graph and use the correct equation. Okay, so let's do the first part from -5 to 0. So heating the solid from -5 to 0, it's mass, 12 grams. Delta T is 5 degrees. 0 minus a -5 is 5, and it's 2.09 joules per gram degrees Celsius. And notice that if you're using the right equation, everything should cancel except for joules. So the grams will cancel and the delta C will cancel, and we find out that it's 125.4 joules of heat. And you could go ahead and convert it to kilojoules. You'll see in a minute that we have to add them together and they have to be all the same unit. But at this point, you can leave it at 125.4 joules required to heat ice from -5 to 0. Then we have to melt the ice. Notice that delta H for the melting is kilojoules. The constant is kilojoules per mole, which means we have to multiply by moles. So the first thing we have to do is convert, and you can see up in the right-hand corner, 12 grams, 18 grams per mole is 0.667 moles. So 0.667 moles times 6.02 kilojoules per mole means that it requires 4.02 kilojoules to melt 12 grams of ice at 0 degrees. Then finally, we have to take the liquid, once it's all been melted, we need to heat that liquid from 0 to 1 degree. So again, this time it's mass times delta T times the specific heat of water, which is 4.21 joules per gram degree Celsius. Again, the grams will cancel, the degrees Celsius will cancel, and we get 12 times 1, because it's only, if we raised it to 50 degrees, delta T would be 50, but in this case it's just 1 degree, times 4.21 joules per gram degree Celsius gives us 50.5 joules, which is the same as 0.0505 kilojoules. So notice the total delta H, you have to add these three together. So 0.1254 plus 4.02 plus 0.0505 to the correct significant figures gives you 4.20 kilojoules is required. So you have to have all those different parts.